All right. Good afternoon. So, yeah, I had initially thought that this was going to be the first full week of lectures without me being away, but I'm actually going to be out Friday for a workshop. So that will, I think, be the last of the recorded lectures. And then next week, Monday is off. So we're still waiting for that week of you getting to see me 3 whole times. But we'll get there eventually. So for the past few lectures, we've been talking about MaxFlow and all of these interesting algorithms for solving the MaxFlow problem. And now that we've really kind of cracked that problem, we're going to make the problem harder. And we're going to talk about min-cost flow. And generally, people just call it min-cost flow. And the fact that you're looking for a maximum flow is implicit. So the idea here is that we have a standard flow problem. With all the usual stuff, capacities, UV, source and sink. And the balance and conservation constraint, the balance and capacity constraints. Okay, but now we add costs. Okay, and this is a per unit cost of flow. Okay, and once we've defined edge costs, we can define the flow cost to be the sum over all of the edges of the flow on the edge times the cost on the edge. Okay? And the min-cost flow problem simply says that among all the max flows, you want to find the cheapest one. Okay. Now, I'll emphasize that the costs can be negative. In certain problems, you actually get a profit for shipping a certain commodity over an edge. We are going to be using a lot of the infrastructure that we've developed for solving flow problems, right? With regard to these costs, I mean, we have flows. We know that residual graphs are very important, right? So when we send flow on an edge, it creates a residual edge, right? And we know that the capacity of that residual edge should equal the amount of flow that we're sending, and that residual edge represents removing that flow, right? But now that we also have to give that residual edge a cost, right? So what should the cost of that residual edge be? Yes? Exactly, right? If the reverse residual edge represents removing flow from the forward edge, then the cost of that removal is what you get back by taking that flow away. So it's just the negation of the other cost. Okay? Now, it's also easy to tackle the problem of finding the min cost to send a given amount of flow. Okay, again, the problem is usually formulated as the minimum cost maximum flow, but what if I want to ask you about the minimum cost way to send 10 units of flow? I claim that I can transform that into a min cost max flow problem. Anybody see how to do that? Yeah?
Just connect this source with this amount of flow that you want.
Exactly. I just create a new source. I add one edge with the desired capacity, and I direct that to the new source, to the original source. And now a maximum flow in this graph will send exactly the right amount of flow. So you can solve that problem the same way. Now, clearly, the min-cost flow problem is a generalization of the maximum flow problem, because anytime you solve a min-cost flow, you are, by definition, finding a max flow. But there's another well-known problem that the min-cost flow generalizes. So suppose that I give you a graph and ask you to solve the problem of finding the cheapest, a graph with unit capacity edges, and I ask for the cheapest way to send 1 unit of flow from S to T. How would you answer that question? Yes? Exactly. So okay, so the cheapest way to send 1 unit of flow in a graph with unit capacities is to send it on a shortest path. Okay? So it generalizes these two problems, and by the time we finish looking at min-cost flow, we'll see that it actually is basically just the exact combination of these two problems. That min-cost flow is max flow with shortest paths, if you understand it the right way. Okay, but we're going to have to develop some machinery in order to see that. So since it generalizes max flow, we can immediately talk about flow decomposition, right? The min-cost max flow decomposes into a set of at most m paths and cycles. But now we also need to talk about the costs, right? So the cost of the flow is equal to the sum of the path and cycle costs. And what do I mean by a path cost or a cycle cost? Well, there's you look at the length of the path or the length of the cycle, and then you have to multiply that by the amount of flow that is on that path or going around that cycle, right? And you add those things up, and you get the overall cost of the flow. Because flow and min-cost flow are linear problems, right? They decompose in this additive way. And looking ahead, starting on Wednesday, we're going to start studying linear programming, and we will see that min-cost flow and max flow are both instances of linear programming problems. So we're heading towards this more general type of problem and thinking about how to solve it. So far, we haven't really said anything new. We've just sort of refined our definitions to go with min-cost flow. There is another way, once we introduced costs, that min-cost flow is actually kind of simpler than max flow. So there is a problem called the min-cost circulation problem. And a circulation is a flow with balance everywhere. So there is no longer a source or a sink. Okay? And when you're talking about max flow, circulations don't, like, they're distracting. They don't solve the problem at all. Okay? But once I introduce costs, min-cost circulation becomes meaningful. Right? It's not trivial, and it's interesting. Right? Now, there's a certain case where it's trivial. right? If all of the edge costs are positive, then what's the min cost circulation? Yes?
It's very positive, so you don't want it.
Right. If the edge costs are positive, then any circulation is going to cost something, and so you don't want it. So the optimum min cost circulation is 0. But if there are negative edges, then the min cost circulation problem becomes very interesting. Okay. It's obviously closely related to the min cost flow problem. And in fact, I'll show you in just a minute that you can transform any min cost flow problem into a min cost circulation problem and vice versa. So we can study either one. And because there's no source in sink, the min cost circulation problem is actually more elegant and often requires less notation. One way it is more elegant is decomposition. What does a circulation decompose into? Yes? Only cycles. No more paths. So again, that's part of what makes it simpler. Okay? So let's talk about reductions between min cost flow and min cost circulation. And these are important reductions. They're not just thought experiments. There are algorithms that really work only for one of the two problems, or sort of are really tied to one of the two formulations. And so you need to do these transformations in order to apply these algorithms. So if I have a min cost circulation problem, how do I reduce it to a min cost flow problem? That is, how do I create a min cost flow problem whose answer also gives me the answer to the min cost circulation problem? Yes?
Make the source a sink.
What was that?
Make the source also a sink.
Make a source also a sink. So I could take this graph, and I could put a thing in here and say, this is S and T. Right? That would work. It's a little nervous because, in a sense, I can send infinite flow. So the amount of flow is not really necessarily defined. So that, I mean, it probably wouldn't be a problem for most algorithms, but any other suggestions that might avoid that problem? Yeah? Yeah. What I can do is I can just say, OK, here's my source. Here's my sink. Find me a min cost max flow. Right? What's the max flow from S to T? Well, there isn't any. It's 0. But you still need a min cost version of the 0 flow. And so that will force you to find a min cost circulation in the rest of the graph. OK? So it's cheating, but it's not cheating. It's correct. Now how about a reduction from min cost flow? So now I'm given a min cost flow problem, and that means I have an S and a T. But my algorithm is a min cost circulation algorithm. So how do I turn this flow problem into a circulation problem so that I can give it to my circulation algorithm? Yes?
Maybe connect T to S with like a very large control part.
Great. So if I make the cost of this edge minus infinity, then any circulation is going to be highly motivated to use that edge. Right? Now, I also need a capacity. What capacity should I give it? I heard somebody say it maybe, but I couldn't. Infinity, exactly, right? Right? That ensures that I'll never run out of capacity, and so I can use as much as the circulation wants. Okay? So what this is essentially saying is, whatever flow you're able to send from S to T, we can get it all back to S using this edge. Right? And so the cheapest way to do that, to send it all to T and get it back to S, would involve using the minimum cost flow from S to T, and then you add in what you get back, then you just send it back to S. Now, it's a little shady to use infinite numbers in a computer. They don't fit in machine words very well. Might we be able to just use a number that's big enough? Yeah? Good. So we can put a bound on the amount of flow equal to, at most, the capacity of edges leaving S, right? Now, I don't want to start special casing simple graphs anymore, so I'll say, well, maybe all of the edges are leaving S, right? But it's still only M edges. Each of them has some maximum capacity, which I wrote as capital U, right? So that's an upper bound on the capacity of what can leave S. It's upper bound on the amount of flow that needs to be circulated back, okay? What about the cost? Good. So for each edge, I have a certain cost per unit flow, right? So so what could go wrong if I make C not negative enough? What could go wrong? Well, I might have some flow that is really expensive to send from S to T, and it isn't worth it to send it and then bring it back. So how do I make C big enough or negative enough so that it's always worth it to bring the flow back? Yeah?
So the maximum the flow can cost from S to T, where I guess I've gotten that would be the number of edges times the maximum capacity times the maximum cost.
Great. So what we can think about is that whatever that flow is doing, it's traversing some. We can actually use the path decomposition, right? So the flow is traversing a path, right? And each unit of flow on that path costs something. And I need to make sure that the return brings more profit than the cost. Right? So remember, this is a per unit cost. So I need to outweigh the per unit cost of sending the flow from S to T. A given path is at most going to have n edges on it, right? Or is going to have less than n edges on it. And so I can, again, define some upper bound C on the individual edge capacities, right? And so if every edge is at most C, then every path will be at most n minus 1c, and so if I use minus nc as the return cost, it means that I make money by sending flow to S, from S to T and then bringing it back to S.
So for the mean cost circulation problem, I want to make sure that I understand the problem well. So you said there are some really expensive cycle that you want to, you also want them to flow, right?
Because I'm requiring a max flow, right? So you don't. So again, we're doing a reduction here, right? So the point is that I'm assuming that I am given a min-cost circulation algorithm, right, which has no definition of max flow, right? But I want to force the min-cost circulation algorithm to give me a max flow, which means I want to force it to use even those very expensive flow paths. And the only way I can force it is through cost, because the circulation does not have any notion of amount of flow. It only cares about the cost of the circulation. Okay? But by making a very cheap edge from T to S, that means that any path of flow from S to T is worth using to send flow, because I make more money on the return edge than I do on the path from S to T. Yes?
Doesn't even make it practical, right? You don't want
Exactly, right? And because the site, right, remember, this algorithm is trying to minimize the cost of the circulation, right? So if you have a path from S to T, right, and then a return edge, that creates a cycle. And since the return edge is more negative than the whole path, the overall cost of that cycle will be negative, which means that I will make money by sending flow on that cycle. And so the min-cost circulation algorithm will do that. It will not leave any capacity from S to T, because if there's any capacity from S to T, then there's a path from S to T, and I can make money by circulating from S to T and then back to S. Yes?
Circulation during some other cycle.
Yes. Well, so, I mean, this will become more clear as we do some of our reductions and things, right? But all we have to say at this point is that whatever the min-cost circulation does, it will not leave any capacity available from S to T. Because if there is capacity, then the min-cost circulation algorithm could get better by using it. Okay? So whatever it finds will be a maximum flow. Okay? And if you're not sure about that, again, wait until a couple of the reductions that I'm going to do. Okay? Okay, but let me give you another reduction. So this reduction is a little bit annoying because you end up creating an edge whose capacity is like, maybe I start with a graph where C and U are both 1, right? The unit capacity, unit like cost case. And all of a sudden, I've got these polynomially large capacities. That's a little disturbing if you're thinking about things that, like we had algorithms that were better when we had unit capacities, and all of a sudden we would not have unit capacities. So here's another reduction. Okay. For going from min-cost flow. So what we do is we find any flow F. Okay? We're trying to find a min-cost flow. We start by finding any old flow. Okay? Let's consider the actual min-cost flow, F star. Okay? And these are both from S to T. Right? Yes. Sorry, any max flow. Okay. So now we have two flows from S to T. I claim that the difference of these two flows, right? You take every edge and you subtract from the flow F star the amount of flow that F is using on that edge. What do I get if I subtract two ST max flows? It's a circulation. Okay? Essentially, right, negating F is basically sending flow from T to S, sending in the reversed graph, sending a maximum flow, actually, in the reversed graph. And so what this is doing is sending as much flow as possible from S to T and then sending it back by a different route. Okay? I claim that it is feasible in the residual graph of the flow. Okay? So essentially, F star was feasible in G by definition. Okay. So F star minus F, where I take away F sub E units of flow on every edge, is feasible in G minus F, where I have taken away F sub E units of flow from every edge. Everybody happy with that? Okay. And I mean, this is also, like, you have to sort of think about the residual edges and such, right? So in G sub F, I may be creating some capacity, right, which can now be used in F star. And so what that means is basically, right, any flow that I find is is a circulation away from the min cost flow, right? So F star, the min cost flow, is equal to F plus a circulation. Yes? And that means that the min cost, F star, is equal to F, which has a fixed cost, plus the min cost circulation. And so another way to solve min cost flow using a min cost circulation algorithm is to first find a max flow and then find a min cost circulation in the residual graph. Does that make sense? So first you maximize the flow, and then you adjust the cost. All right, so this is actually the first step towards what I said right at the beginning, that max flow that min cost flow is max flow plus shortest path. So here we see the max flow happening first, and then there's this cost adjustment that we need to do, and we'll see that that is very closely connected to shortest paths. Okay? All right, so now we've got sort of the basics of the structure of the problem and how it relates. We also have the answer to this really important question of why we didn't use C for capacities, right? Okay, we were holding in reserve. Now you might think, wait a minute, why did I have to use C? Why did I have to talk about costs? I could have talked about, say, prices and used P for prices, and then I would have had C for capacity. But it turns out we need to hold P in reserve for something else. So we'll come back to that. All right, so now that we have this sort of formulation, we're going to start thinking about how to solve this problem in the same series of steps that I talked about last time. That works generally for combinatorial optimization. So before we try and construct an optimal solution, let's try and figure out how to detect an optimal solution or to verify an optimal solution when it is proposed to us. Right? So suppose that we're given a max flow. How do we decide if it is a min cost max flow? Well, let's look at this reduction. Okay? This says that the difference between flows is a circulation. And that, like, if you're going from a flow to a min cost flow, the way to do that is through a min cost circulation. So if you're already starting with the min cost flow, what does that tell us about this reduction? Yes? Right. So the max flow is optimal if, according to this reduction here, the residual min cost circulation is at least 0 in cost. Right? If you're given this max flow, you know that the way to get to a min cost max flow is to find the min cost circulation and add it in. Right? And so if your current max flow is optimal, then you can't improve your max flow by adding a min cost circulation, which means that the min cost circulation must be non-negative. Yes? Okay, so that is nice, but it's kind of hard to work with, right? We don't know how to find a min cost circulation yet, so it's not a very good step for verifying optimality, right? So can we simplify our verification in some way? Yes?
You might just be able to test for negative cycles.
Great, right? So imagine that we decompose this circulation into cycles. Okay. In order for the min-cost circulation to be negative, it would have to have at least one negative cycle, right? Okay. And so that's a much easier criterion to verify, right? I now can state my claim that my flow is optimal if and only if there is no negative cycle in the residual graph. And so let's double check that in both directions. So suppose that I have a flow, and there is a negative cycle in the residual graph. How do I know that that flow is not optimal? Yeah?
Add that, use that, that negative cycle that I found to make my flow cheaper.
Exactly. If there is a negative cycle, then pushing flow on it decreases the cost and shows that that the flow is not optimal, right? Conversely, if we're non-optimal, right, that implies that the min-cost flow is less than 0 by this reduction we did over here. And that means that if you decompose it, you get a negative cycle. And just to emphasize, I am again using this concept of zero capacity edges being not there. So when I talk about the existence of a negative cycle, I mean the existence of a negative cycle with capacity. Right? A cycle with zero capacity is not meaningful. You can't use it for flow. Okay? So this is a very simple and easily testable criterion for deciding on the optimality of a min-cost flow. But how easy is it to test? How do we test it? So testing optimality by seeking a min-cost cycle. So how do we find a min-cost cycle? Yes?
Bellman-Ford.
Bellman-Ford is an example. So more generally, and again, this comes back to this thing that I said at the beginning, min-cost cycles are intimately tied to shortest paths, right? So if there are no min-cost cycles, then shortest paths exist, right, between any reachable pair of vertices, right? Because the shortest path is a simple path. It's never worth going around a cycle. And so one of them is the shortest. However, if there is a negative cost cycle, then if you can reach it on your way from S to T, then you can go around it as many times as you want and make your path from S to T as cheap as you want it to be. All right? So I shouldn't say negative cost. So you have a negative cost cycle if and only if shortest pass break. Okay. And so we can use, for example, Bellman-Ford. Right? Which is an order mn time algorithm. And that becomes the time that it takes to verify a min-cost flow is optimal. Okay? Now, why didn't I suggest using Dijkstra's algorithm? Yes?
Dijkstra's algorithm doesn't work with negative.
Right. So negative edges are a problem for Dijkstra. Okay. Now, they're not an insurmountable problem for Dijkstra, actually. There is a scaling algorithm that generalizes Dijkstra's algorithm. And you can use that to verify a min-cost flow in m root n log c time. Okay. So not as good as Dijkstra, but definitely better than Bellman-Ford. Okay. Okay, that's testing for optimality, but that also gives us a first step towards achieving optimality. So, you know, we now have a detector for a non-optimal flow, right? So how can we turn that detector into an algorithm for finding a min-cost flow? Yes? Right. What we will do is simply repeat, find a negative cycle, and then cancel it. Okay? Everything is about cancellation these days. This is known as Klein's cycle canceling algorithm. Which just goes to show you that in the old days it was much easier to get your name on an algorithm. Okay. And of course, the hard part here wasn't defining the algorithm, it was understanding the infrastructure that would make this algorithm correct. Okay. What can we say about the speed of this algorithm? Well, this algorithm is definitely not strongly polynomial. So let's already recognize that we're going to have to use the max cost and the max capacity in the runtime. But what is the dependence on these quantities and on the graph size? Well, so here again, it's about understanding what sort of progress, right? What sort of progress does a single cycle canceling step take towards optimality? Yes.
So I mean, I guess it kind of again depends on if we're dealing with integer flows.
Yes. So remember, anytime I say that we're talking about C and U, I'm implicitly talking about integer quantities.
So I mean, we can push at least one flow if we know that it's not negative, and that flow will improve our cost by. So if we push this one flow, then we will improve our cost by the negative cycle cost.
And what can we say about that negative cycle cost?
Well, if it's negative, if it's also, I guess, going to be an integer, and so it must be at least -1.
Right. Every cycle says at least one. I mean, again, we're seeing integrality, and as with the standard augmenting paths algorithm, right? If we start with integer capacities, then when we cancel a cycle, we still have integer capacities. And we send at least one unit of flow through the cycle. And it's a negative cycle, which means it's -1 or less. So we decrease the cost by 1. Actually, I should say, this is actually a min-cost circulation algorithm, right? If we're just looking for cycles, and we're not actually changing the amount of flow going anywhere. We're just moving the flow around, right? So, but we can use the reduction that I described over here, right? Basically, we find a max flow first, and then we turn it into a min-cost flow using Klein's cycle canceling algorithm. Okay? So we make progress. How can we relate that progress to the total amount of progress that we might have to make? Can we bound something? Yes.
You know that you could find like the minimum cost for all the edges, and they'll never be smaller than n times that.
Exactly. We can basically look at each edge and say, what's the least, what is the greatest profit, right? The most negative cost that could possibly be pulled out of that edge. And the answer is if you saturate that edge and it's maximally negative, in which case you would be getting minus CU from that edge, because you'd be sending U units of capacity through negative C cost. And there's M edges. So the minimum possible cost is minus MCU. Okay? Which is a very important acronym these days, right? Okay. Just shows the foresight of researchers of the past decades. So we now know the time to find a negative cycle using Bellman-Fordor-Dijkstra. We know how many of those negative cycles we'll need to do. And so overall, our runtime is order nm squared cu, or order, with some logs, m squared root n cu. So we have some pseudo-polynomial bounds. They're kind of big pseudo-polynomial bounds, but we have something. Okay, so this was our first algorithm. And if you think about it, this is basically the analog of the generic augmenting paths algorithm, right? With MaxFlow, if you weren't maximal, there was an augmenting path. You found any one of them, and you sent flow on it. Here with min-cost flow, if you're not optimal, there's a negative cycle. You find any one of them, and you send flow on it. So it's really analogous, and it's just as weak, right? So in order to solve better, we're going to need to introduce some more powerful ideas. And this is where we really sort of, there's some new conceptual stuff now for min-cost flow that has no relation to, that has no roots in MaxFlow. But since we're gearing up for something conceptual, this might be a good time for a 2-minute break. So get up, get the blood moving, and remember, if you're sitting, it means you don't need a break. All right. So back to max flow. So we're now going to look for another way to demonstrate the optimality of a min-cost flow or circulation. Again, whether you started with a min-cost flow or circulation problem doesn't actually matter, because what you're actually trying to demonstrate is the optimality of the residual graph. You want to show that it has no negative cycles, and it doesn't matter where the residual graph came from. Okay? And the technique that we're using is based on something known as LP duality, which we'll see next week. And you know, what we've been talking about until now is this approach which says, you know, here's a graph, and I want you to stand back from the whole graph and compute the optimum thing for every part of the graph to be doing. So if you think about it, this is kind of a command economy, right? You send flow here, you send flow there, right? I'm just sort of defining the entire structure of the flow in the graph, okay? But this is America, right? We love capitalism, right? So let's take a more capitalistic approach to the min-cost flow problem. So instead of trying to plan things all out in advance, right? So okay. And I'm going to do a min-cost flow, not a min-cost circulation to start with, just to make things easier to think about. So I've got my S and my T. And what I'm going to do is I'm going to think of something that people really want at T. Okay, so what's something that MIT students really want these days? Coffee, beer, I'm not sure. Is Red Bull still popular? I mean, what's the drink of choice these days? Boba. Okay. So at T, there's a large demand for boba. So what I'm going to do is I'm going to give away boba at S. All right? So what is going to happen if I start giving away boba at S, and there are all of these MIT students at T who can't leave because their exams are coming, right? So they're stuck at T. So what's going to happen? Uber, right? And other competitors, merchants, right? So you can imagine now that there will be merchants who can buy and sell boba at the vertices, the different cities where transactions can occur. And they can ship it over to the edges at the costs that are defined by those edges. Okay. So this is going to create a market. Right? And if everybody is sort of busy buying and selling and shipping things, it is going to establish certain prices at the vertices. Okay. And I'm going to denote these by PV, which is why I couldn't use P before for the edges. Okay. So the question is, what determines these prices? What prices are stable? So suppose that I'm given a particular piece of V, price for boba at V, price for boba at W, and a cost for shipping boba from V to W. What different outcomes are going to occur depending on these prices and costs? What merchant behavior will be driven? Yes?
Yeah, so if CW or CVW is less than the difference in prices at V and W, then the merchant will use like the entire capacity of the edge.
Good. So there is an opportunity for somebody to buy boba at V, ship it to W, and sell it at W. Right? So if PW is larger than PV plus CVW, then a merchant can profit by doing this kind of shipment. Right? So anytime you've got this misalignment where the prices mismatch, a merchant can try shipping stuff. And this means things are out of equilibrium, right? So if the merchant just buys a ton of boba at V, it may raise the price there. So PV will increase, right? That's one way that you could recover equilibrium, right? Another thing is if they're selling too much at W, PW could decrease, and that could bring you back into an equilibrium, right? But what else could prevent the merchant from profiting on this shipping? Yes?
If someone else does the same thing.
OK, so it is true that a different merchant could come in and interfere with our first merchant. But from our perspective, where we just want the boba to get to T, we don't care, right? What we care about is that there be a sort of an efficient market happening that moves the stuff, and we don't care which merchant does it. So what could happen that could stop any merchant from making a profit off of this route? Yes?
The flows are saturated.
Saturation, right? Unless VW is saturated, i.e., there is no residual capacity. Okay? And so this observation leads to the following definition. We say that the prices PV are feasible for a given residual graph. So we might say they're feasible for a given flow or feasible for a given circulation, by which we mean for the residual graph that is left. If and only if, oh, sorry, doing things in the wrong order. Let's back up one step. So this quantity that we're interested in, right, PW being greater than PV plus CVW. I'm just going to move PW over to the other side. I'm going to define the reduced cost of VW to be equal to the cost of the original cost of the edge plus the price at V minus the price at W. Okay? So this is, if you think about it, how much it will net cost a merchant to buy the stuff at V, ship it to W, and sell it there. And notice that this phrase is a cost. Okay? So the problem, the lack of equilibrium, is when this cost is what? Yeah? When it's negative. Right? A negative reduced cost is a sign of instability. Okay? And so now I can put up that other definition. A set of prices is feasible for a residual graph if no residual arc has a negative reduced cost. Okay. If no residual arc has a negative reduced cost, then there is no incentive for any merchant on any edge to do any buying and selling beyond what's already happening, right? Presumably the residual graph that you have is a result of some activity, but having these reduced costs means that having this feasible price function means that there is no additional activity. And so there will be no change to the prices that you are currently observing. So any questions about the definition? Let me point out something interesting. The prices don't affect the overall cost of a circulation. Okay? So I'm basically giving some new costs to the edges, right? Each edge had an old cost. Now I change it by PV minus PW. Why does that not change the cost of the circulation? Yes?
When we sum through all the arcs, those additional PV and PW's telescope.
Exactly. So the point is that a circulation is a sum of cycles. And on a cycle, the price changes telescope. Right? Essentially, if you buy something and then ship it around a cycle and then sell it back where you bought it, obviously the price along the way didn't matter, right? And you pay the same amount for the shipping. Okay? So putting in these prices doesn't change the cost of a circulation at all, and they change. Sorry, let me add a header here. Prices change all max flow costs by the same amount. And that means that the min cost flow is the same flow. Why is that? Yes?
Because every cost on the way is cancelled out. The same amount is the cost of S and the cost of T. And for
Exactly.
Any flow.
Exactly. So again, we can think about decomposition. We've already taken care of the cycles. What's left is the paths, right? On a particular path, right, you're just buying and selling. You're just selling the boba at every vertex and buying it right back. And so you're not paying any of the intermediate costs. All you're doing is paying to buy the boba at S and sell it at T. And you pay the same. You pay that P of S minus P of T for every unit of flow that goes from S to T. And so it doesn't matter how the flow goes from S to T. Right? Every flow changes by the same amount. Every max flow changes by the same amount. Okay? So now we're on to something. This gives us a lovely way to prove optimality of a residual graph. A residual graph, that is the circulation that creates a residual graph, or the flow that creates a residual graph, is optimal if and only if there exists a feasible price function. The proof is very straightforward, given what we've already said. So suppose you have feasible prices PV. Okay. How do we prove that our residual graph is optimal? Well, what was our previous criterion for deciding that a particular residual graph was optimal? No negative cycles, right? So if we can conclude from having a feasible price function that there are no negative cycles, then we're done, right? So if we have a feasible price function, this implies that all the reduced edge costs are non-negative, right? So what's the next step? Why? Sorry, go ahead.
Well, yeah, I also want to answer, because like, we said that the price of the cycle stays the same.
Exactly, right? The reduced costs are non-negative. That means that the reduced cycle costs are non-negative, because you can't make a negative cycle out of positive edges or out of non-negative edges. But the original cycle costs are the same as the reduced cycle costs. And so the original cycle costs in this residual graph are also non-negative. And therefore, the residual graph is optimal. The circulation or flow that produces this residual graph is optimal. Okay? And so again, what's critical here is the way that the prices telescope, the cost telescope under these price functions. So now, the trickier bit, let's suppose we have an optimal flow or circulation or the residual graph of them. Okay. We now need to demonstrate that there is a feasible price function. How can we do that? Shortest paths, yes. Right? So we there's sort of a hint that we need to use shortest paths, right? Because what we know from having an optimal first feasible flow circulation is that there are no negative cycles in the residual graph, right? And the one thing that we know about graphs with no negative cycles is that you can compute shortest paths in them. So that must be useful for something. So let's compute shortest paths from the source. Okay. And let's just call them P sub v. Okay. So the price we set on vertex v is the length of the shortest path from S. Now, why does that make sense as a price? Yeah?
The cheapest way, so we kind of, to ship it to V, we have to pay all the costs on the way, so basically the cheapest.
Exactly. Exactly. The shortest path is the cheapest way to get boba from where it's free, in that magical land, right, to where you want it. Right? So it's the price of a unit of boba. So the question is, I mean, these are very natural prices to talk about. Can we prove that they're feasible? triangle inequality, right? So the definition of shortest paths is that they satisfy triangle inequality, which says precisely that the price at W is at most the price at V plus the cost of edge VW. And so if we go back and look at the definition of a reduced cost, right, CVW plus PV minus PW, this is denoted as putting a superscript P on the edge. And that's defined to be CVW plus PV minus PW. And it's going to be greater than or equal to 0. Okay? So, really crucial theorem. Question?
Sorry, do the shortest paths that we're talking about necessarily exist?
No, and that was going to be my next question. Do the shortest paths necessarily exist? See, that's going to be my next question. So, right, what I did was very intuitive, but we do have to worry about one little detail, right? What could stop a, why have I not sort of fully defined what happens? What was that? Yeah, I could have a graph that's not connected. I could have things that are not reachable from S. So what can I do about that? You might think I could say, well, vertices not reachable from S don't matter, right? Because I can't send flow. That doesn't quite work here because we're all about circulations now, right? There might be a whole circulation reachable from S. There might be a whole negative circulation reachable from S, not reachable from S, right? Which would still violate our optimality. So how do we fix that? Yeah? Exactly. What we do is we have our vertex S. We just create an S prime that reaches everything with edges of length 0. Essentially what we say is, we'll give Bobo away everywhere. Yay. Okay. And the point is, if there's a negative cycle, right, then the people who are getting that boba on the negative cycle can make money by sending the boba around the cycle, right? So the absence of a negative cycle means that in this graph, there will be shortest paths, right? Now, the fact that there are 0 cost edges everywhere means that all the prices that I find will be at most 0. But that's OK, right? All my prices will be negative, but they will still satisfy the triangle inequality. And therefore, they can still be used to adjust, to create reduced costs that are all positive on the edges, or all non-negative on the edges. Okay. All right, so this is now really cool. We have a new optimality condition, a new way to verify optimality, which is to simply say, all you have to do is give me a feasible price function. Okay. So to verify optimality, somebody just has to give me a feasible price function. if the person who is claiming that this is a min-cost flow also gives me a feasible price function, how hard is it for me to test their assertion? Remember, before we were talking about looking for a negative cost cycle using Bellman-Ford and taking order mn time. Right? Now, if somebody gives me the price function, how quickly can I verify optimality? Yes?
O of n.
How?
Just check each edge.
Exactly. Just compute the reduced costs. And check they're at least 0. Right? And so this is order m. So the prices are a certificate that make it really easy to check the optimality of your solution. Well, sorry, you have to give a feasible price function. Feasible is the definition of correct, right? If I give you any old price function, it doesn't tell me anything, right? But if it's a feasible price function, then the reduced costs that I compute are all non-negative, and that immediately tells me, it tells me two things, right? It tells me that the flow is optimal, and it also tells me that the price function is feasible. So these two things actually certify each other. Okay. The other thing to notice is that you can find the feasible price function via a shortest path computation. Okay. And so this really starts to get into this point that I made at the very beginning, that min-cost flow is just max flow plus shortest paths, right? Once you have your min-cost flow, all you have to do to verify it is a single shortest path computation, and out comes this really nice certificate. Okay. So this price function, we will see next week, is an example of an LP dual, okay? And it plays a role kind of like the min-cut did to max flow, okay? These are two things that sort of verify each other's optimality, right? So when we had a max flow, we knew that we knew that we could demonstrate a max flow by showing you a min-cut that had exactly the same value, right? And since the min-cut always upper bounded the max flow, when they matched, we knew that both of them were optimal. In a similar way here, right, the flow, the min-cost circulation or flow, and the price function certify each other's optimality, right? The fact that, that you have both of them lets you see that both of them are optimal. Now, it's easy to understand what optimality means for a min-cost flow. I haven't really talked about what the optimality of a price function is, and that is something that will emerge through our study of linear programming. But it really does play the same role. Okay. So now we've really nailed the question of verifying a min-cost flow, right, with this very elegant appeal to price functions. What we'll see next time is how you can leverage the price functions to steer better algorithms. And I will give you some polynomial time algorithms for min-cost flow that rely on the price function not just to verify optimality, but actually to tell the algorithm how to go find that optimal solution. Okay? Any questions? Okay, then I will see you Wednesday for the first time in God knows how long.